Let's try it like this. There we go. All right. Okay, good morning, or I suppose good afternoon. It really depends on what time you guys are going to watch this. Today, we are going to pick up where we left off on Monday, talking about infinite series. Now, unfortunately, I'm recording this on Sunday evening, so it's not 100% clear to me where we're going to get to on Monday. But I'm going to do my best to make this tie in with where that lecture usually leaves off. So, without further ado, let me get the dot cam fired up and we'll get into it. Okay. Here we go. Focus, you fuck. All right. So this is MAC2312, and this is the lecture video for 10/21/20. Today, we're going to talk more about infinite series. Specifically, we're going to address sections 11.3 and 11.4, which are on the integral test and comparison tests. And comparison tests is indeed plural. There is more than one comparison test for infinite series. For some reason, my left hand is cramping pretty brutally here. We'll get through it. Okay, so before I do that, I want to just recall some of the basic facts from Monday. If you have the infinite series S, which is sigma an, and you could sum from 0 or from 1, but it always goes up to infinity. This whole thing here is a series. The an's, the thing inside that are being added up, those are the terms of a sequence. And this capital sigma notation is a shorthand for a big addition problem. So this would be A0, because we're starting at n equals 0, plus A1, plus A2, plus A3. And we go on and on and on until you get to whatever the number is up here. And in this case, because it's an infinite series, the upper limit here is infinity. So this series just goes on forever. It never actually ends. And we write that with the 3 dots. The series capital S, because it's hard to define, it's an infinite addition problem, we defined in terms of the sequence Sn. So this was the sequence of partial sums. S0 is A0. S1 is A0 plus A1. S2 is A0 plus A1 plus A2. And you get the feel. S3 is A0 plus A1 plus A2 plus A3, and so on. And the big deal for infinite series is that the full infinite series S is equal to the limit as cap n goes to infinity of sigma n from 0 to cap n of an. And then this guy here, the sigma n from 0 to cap n of an, that's really Sn. S sub capital N is A0 plus A1 plus A2 plus A3 plus A4 all the way out to AN. And you can compare this to the idea of an improper integral, right? The integral from 0 to infinity of f of x is the integral from 0 to r, and then you take the limit as r goes to infinity. So this Sn here is this thing. So this is the limit as n goes to infinity of Sn. All right, and remember the definition of convergence for an infinite series. An infinite series converges if the limit of partial sums exists and is finite. In other words, the infinite series converges if and only if the sequence of partial sums is a convergent sequence. So all of this should be reviewed from Monday. Also on Monday, we developed a few basic theorems. This was our first convergence test called the test for divergence. And this just said if the limit as little n goes to infinity of an, the limit of the an's is not 0, then the series S equals sigma n from, could go from wherever, but I'll say from 0 up to infinity of an must diverge. Okay, and we proved this on Monday. The other big things that we did on Monday were get the result on geometric series and show you a little bit about telescoping series. I want to remind you the result on geometric series because that is so important, and then we're going to get into the new stuff for today. As you watch this video, you may want to pause from time to time because I won't be pausing to take questions in the way I normally do. So it's on you guys to remember to pause, make sure your notes are filled up, and then keep going. So make sure that you're monitoring this. You can play it on like half speed or 3/4 speed if you want to. But again, just because you can't take questions, please don't just let this play without taking notes. Please pause, fill in your notes, make sure everything is good, and then unpause and move on. Okay. So the other big results from Monday, before I do this, let me remind you one other thing. The converse to this is not true. That is, if the limit as n goes to infinity of an is 0, that does not mean that the series sigma an summed from wherever to infinity must converge. That does not mean that this converges. So we call this a one-way implication. If the limit of the an's is not 0, then the series sigma an must diverge. But the other way around doesn't work. If the limit of the an's is 0, it's not the case that the series sigma an then must converge. All right, it only goes the one way, it doesn't go the other. All right. So other important stuff from last time. The theorem on geometric series. This said that the series S equals sigma n from wherever, but again, I'm going to use 0, of some constant a times some other constant r raised to the n. And we could write this out. That sigma notation is shorthand for a times r to the 0 plus a times r to the 1 plus a times r to the 2 and so on forever. It's called geometric. And that these series converge if and only if the absolute value of the number r, which is called the common ratio, if and only if the absolute value of r is strictly less than 1. in that case, the sum of the series is, well, for this guy, it would be A over 1 minus R. And in general, the safer thing to remember, because this series could start anywhere, it doesn't need to start at 0. The starting term could be like n equals 3, which would mean that the first term here is A times R to the 3. The general result is you take the starting term and you divide by 1 minus the common ratio. We worked lots of examples with this on Monday, so I'm not going to go through and do another one. The other type of series that we played with on Monday were called telescoping series. And those were series where you do some partial fractions, you write out the partial sum, the SNs, there's a lot of cancellation, and then you're able to work directly with the SNs. Those are really cool, but today we're working with something new. So in particular today, I want to work with you on something called the integral test. So this is the end of the review. Today I want to cover section 11.3 on the integral test. And if there's time, we might touch a little bit of 11.4 because the integral test usually goes pretty quickly. But we'll see how it goes. So there's a neat analogy. Compare the integral from 1 to infinity f of x dx, which is defined to be the limit as capital R goes to infinity, integral 1 to capital R f of x dx, with the infinite series sigma n from 1 to infinity an, which is defined to be the limit as cap n goes to infinity, sigma little n from 1 to infinity an. These look very similar, and indeed they are very similar. Here I'm adding up all the terms of the sequence an from 1 to infinity, and there's a challenge there because that goes on forever. Here I want to integrate to find all the area under f of x from 1 to infinity, and that's a challenge because it goes on forever. And in both cases, the way we get around it is by defining the infinitely long thing as a limit of a finitely long thing. It's very, very nice. The relationship between the two is, well, one of the major relationships between the two is what we're talking about today, the integral test. So I'm going to tell you what the integral test says, and then we'll play with it a little bit. Here's the statement. So this is our second official test for convergence, right? We have the test for divergence. That's our first convergence test. We have the results on geometric series, although that's not really a convergence test. The next real test, where you're given a series and you want to figure out if it converges or not, so you start running it through these things. The next one you could try is the integral test. This says if an is equal to f of n, where f of x is a function which is positive, continuous, and decreasing, then the integral from 1 to infinity of f of x dx and the series sigma n from 1 to infinity an These do the same thing, meaning if one converges, the other converges. And if one diverges, the other diverges. The way we say that is that they converge or diverge together. Now there are some subtleties to this that I haven't put in here, right? It doesn't always have to be from 1 to infinity. You could go from like 5 to infinity or 10 to infinity or whatever. The function here doesn't always have to be positive, always have to be continuous, or always have to be decreasing, but you need those things to be true from some point on. So maybe for x equals 0, 1, 2, 3, the function isn't decreasing, but then from every x value after 3, it is decreasing. That sort of thing is okay. So you can replace these hypotheses with the word eventually, right? Eventually positive, eventually continuous, and eventually decreasing, meaning from some point on. But for us, we'll usually just work with the basic thing here. A few good examples, fun things to play with using the integral test. I could say investigate the convergence of the infinite series S equals sigma n from 0 to infinity 1 over n squared plus 1. All right, this is an infinite series. It's certainly not geometric because the things I'm adding up here are not like some constant to the n. In fact, I can write out the first few terms, and it's always a good idea to do so. So if I plug in n equals 0 here, I get 1 over 0 squared plus 1. That's 1. If I plug in n equals 1 here, I get 1 over 1 squared plus 1. That's 1/2. If I plug in n equals 2 here, I get 1 over 2 squared plus 1. That's 1 over 4 plus 1, or 1/5. If I plug in n equals 3, that's 1 over 9 plus 1, or 1/10. And the series continues on like that. So remember, the infinite series is what you get by adding up all of these numbers. Adding up all of the numbers that come from this formula with n replaced by 0, 1, 2, 3, 4, 5, all the way up to infinity. Okay, so this is what my series looks like. To go from here to here, here to here, here to here, there's no one constant that I can multiply by, so definitely not geometric. You might hope that you could factor the bottom and do some partial fractions. Maybe it's a telescoping series. But because n squared plus 1 is an irreducible quadratic, we know that we can't factor that and hope to do any partial fractions. If you wanted to set up PFD with this thing, you would just get this thing back. So that's not the move. Which means that the integral test is the move, because that's the only thing that we have besides those. So we're going to use the integral test. And you'll always see me do this. Before I use any test, I always tell the reader what test I'm using. So here I intend to use the integral test, so I write the words integral test. The series here is sigma an, where an is 1 over n squared plus 1. This is equal to f of n, where f of x is 1 over x squared plus 1. So if I want to use the integral test, what I need to show is that this function is positive, continuous, and decreasing. Now, all of these are things that can happen differently at different places, right? Some functions are positive over here, but not positive over there. Some functions are continuous on the interval 0, 1, but are not continuous at x equals 5. What we really need to show is that this is true, that these three things are true for the values of x that we're considering. Now, if the values of x that I'm considering here are coming because I'm thinking of this thing as being in this series, that means I need to show that these properties hold on the interval from 0 to infinity. And if this sum was being done from 10 to infinity, this would be the interval 10 to infinity. Okay, so positive. Is f of x positive? Well, f of x is 1 over x squared plus 1. This would be greater than or equal to 0 if and only if, let's see, the top, sorry, let me bring this up. The top is certainly always greater than or equal to 0. So this would be true if and only if the bottom is positive, right? I mean, a fraction is positive if the top and bottom have the same sign, either both positive or both negative. Here, the top is always positive. So this thing will be greater than 0 if the bottom is greater than 0. But this is always true. Every real number x that you plug into x squared plus 1 gives you something positive. All right? Because x squared is greater than or equal to 0, which means x squared plus 1 is greater than or equal to 1. So, you know, squares are positive, or at least non-negative, which means x squared plus 1, this thing, is definitely always greater than or equal to 0 because it's greater than or equal to 1. So positivity, check. Continuous. Is this function continuous on the interval 0 to infinity? Yes, it is. So 1 over x squared plus 1 is discontinuous only where x squared plus 1 is equal to 0. Right? It's a rational function, ratio of polynomials. Those are continuous everywhere except where the bottom is 0. Well, x squared plus 1 is never 0. This has no real solutions. So yeah, f of x equals 1 over x squared plus 1 is continuous, not just on the interval 0 to infinity, but everywhere. So it's a big old checkaroonie. The last thing we need to look for, sorry, this is here from a previous thing. The last thing we need to look for is whether or not the function f of x is decreasing. So f of x equal 1 over x squared plus 1. I want to know, is this function decreasing, at least on the interval 1 to infinity, or sorry, 0 to infinity. This has derivative, and you can check this yourself. I'm differentiating x squared plus 1 to the negative 1, so that would be negative 1 times x squared plus 1 to the negative 2 times the derivative of the inside is 2x. So this derivative here is negative 2x over, did I do that right? Negative 1 times x squared plus 1 to the negative 2. X over x squared, yeah, x squared plus 1. Yep, good. All right, sorry, just double checking. So I want to know, is this function decreasing? Is it decreasing on the interval 0 to infinity? F of x would be decreasing if and only if f primed is negative. So is this thing negative on the interval 0 to infinity? And yeah, f primed of x is less than 0 if and only if negative 2x over x squared plus 1 is less than 0. Remember, you're decreasing if and only if the derivative is negative. The derivative is negative 2x over x squared plus 1, so the derivative is negative if and only if negative 2x over x squared plus 1 is negative. And again, because x squared plus 1 is positive, this is true if and only if negative 2x is less than 0, which is true for all x greater than 0, right? You know, divide both sides by negative 2, and you'll get x is greater than 0. So yeah, this function is decreasing on the interval 0 to infinity, because what is this set? X greater than 0. That is the interval 0 to infinity. There's a quick way to show this too. And I want to share this with you because this is the part where most of your time is going to go into these integral test problems, is showing that the function is positive, continuous, and decreasing. This is the reciprocal of an increasing function. That's the lazy man's move. So you can always take the derivative, figure out where it's negative to conclude that that's where the function is decreasing. And as long as this lines up with this, then you're happy. But here we could have also said that 1 over x squared plus 1 is the reciprocal of an increasing function. The reciprocal of an increasing function is always decreasing. Okay, so my function is positive, continuous, and decreasing. That doesn't mean that the series converges. That just means that the series and integral play the same. Therefore, the series sigma n from 0 to infinity 1 over n squared plus 1 converges or diverges together with the integral 0 to infinity 1 over x squared plus 1 dx. So if this integral converges, then this series converges. If this integral diverges, then this series diverges. So the last and most important thing we need to do for these integral test problems is to compute the integral, figure out whether or not it converges. The integral from 0 to infinity 1 over x squared plus 1 dx is equal to the limit as cap r goes to infinity, integrals 0 to r 1 over x squared plus 1 dx. Always our first step with improper integrals is to write as a limit. An antiderivative for 1 over x squared plus 1 is the inverse tangent of x. So we have that evaluated from 0 to r. And that we know is that lim r to infinity, inverse tangent of r minus the inverse tangent of 0. Inverse tangent of 0 is 0. And as r goes to infinity, the inverse tangent of r goes to pi over 2. So the integral converges. I'm not yet done though, because remember, the thing I'm trying to figure out is whether the series converges. Up until this point, we'd shown that the series will converge if and only if the integral converges. Now from here, we've shown that the integral converges. So if you put those two bits of logic together, you can deduce that the series must converge. So we say hence, by the integral test, the series S equals sigma n from 0 to infinity 1 over n squared plus 1 must converge also. All right, that's the game. That's the integral test. It's kind of a pain in the ass to use, if I'm honest. We're going to develop a lot of other convergence tests for infinite series. And once you have a bunch of them, you'll find that the integral test is kind of not one you want to use if you can avoid it, because it takes time to show that the related function is positive, continuous, and decreasing. It takes time to compute the improper integral. All of that stuff is time consuming. And for that reason, we really would like to avoid it if we can. So a little later, I'm going to give you a couple of other tests that you can use a little later in this lecture. And then afterwards, we'll have even more tests. But one thing at a time. So this is our first integral test problem. You may want to pause the video and take a second to go back and ask whether or not you fully understand everything we did. The steps here were, first we had to find the related function. You get that by taking your series here was this, sigma n from 0 to infinity 1 over n squared plus 1. And we wrote down what an is. An is always the thing inside your series. Then we replaced the n with an x to get the function f of x. Then we had to check that that function was positive, continuous, and decreasing. Once we verified that that function, 1 over x squared plus 1, was positive, continuous, and decreasing everywhere on the interval from 0 to infinity, we were able to say that the series and the integral play the same. Meaning if the integral converges, then the series converges. If the integral diverges, then the series diverges. Once we knew that the two things played the same, we say, all right, well, I want to know about the series, and I know how to calculate integrals. So let me calculate this integral. If I learn that this integral converges, then I will learn that the series converges. And if I discover that the integral diverges, I will know that the series diverges. And in this case, the integral converged, so we're able to infer that the series converges. Cool shit, right? Okay, so I've got a couple other important examples. You guys remember P integrals? Well, there's something called P series. A series of the form sigma n from 1 to infinity 1 over n to the p is called a P series theorem. You can probably see it coming. P series converge if P is bigger than 1 and diverge if P is less than or equal to 1. So P series are very similar to P integrals because all infinite series are very similar to some type 1 improper integral, and P series are very, very similar to P integrals. The proof of this theorem follows from the integral test. an is 1 over n to the p. So f of x is 1 over x to the p. I need to show first that f of x is positive, continuous, and decreasing, at least for all the x's in the interval. Here I'm summing from 1 to infinity. So here it's going to be in the interval from 1 to infinity. Positive? Okay, let's take a look. 1 over x to the p is greater than 0. Let's say greater than or equal to, because positive or non-negative, either one is okay. If and only if x to the p is greater than or equal to 0. Or really, I should say greater than 0, right? Again, the top is positive, top is 1. So the whole fraction will be positive as long as the bottom is also positive. But here, the bottom is equal to 0 when x is 0. So I should say when x is greater than 0. And x to the p is going to be greater than 0 if and only if x is greater than 0. This actually depends on p. I shouldn't say only if. It's really just the one direction. But certainly if x is positive, then any power of x is positive, right? That's the idea. So that's a big old check there. Continuous. 1 over x to the p is also a rational function. So it's continuous as long as the bottom isn't 0. X to the p is equal to 0 only if x is equal to 0. Right? If you take a number and you raise it to a power, the only way to get 0 out from that is if the number you started with was 0. You can't square a non-zero number and get 0. You can't cube a non-zero number and get 0. So this thing is continuous as long as the bottom is not equal to 0. The bottom is equal to 0 only if x is equal to 0. So f of x equals 1 over x to the p is continuous everywhere except at x equals 0. And in particular, it certainly is continuous on this interval, right? Because 0 is not a part of the interval 1 to infinity. So, yep. And then decreasing. Here's the lazy man's way to do this. F of x equals 1 over x to the p is the reciprocal of x to the p. And regardless of the power p, function x to the p is increasing on the interval 0 to infinity. Thus, f of x equals 1 over x to the p is decreasing for all x greater than 0. And again, in particular, certainly decreasing everywhere on the interval 1 to infinity. You could also make a derivative argument here. I just wanted to show you an example of this kind of lazier argument, where you say, oh, my function is the reciprocal of a clearly increasing function. Since the reciprocal of an increasing function is decreasing, my function must be decreasing. So now we've shown that my function is positive, continuous, and decreasing. Therefore, by the integral test, the series sigma n from 1 to infinity 1 over x to the p converges or diverges together with the integral 1 to infinity 1 over x to the p dx. And normally at this part of the integral test, you would go on to compute this integral and say, okay, the integral converges, therefore series converges. But this is a special thing. Here, remember what we're doing is we're proving a theorem. We're proving this theorem, that p series converge if and only if p is bigger than 1. P series are things like this. So what I'd like to do is conclude that my series converges if and only if p is bigger than 1. What I've done so far shows that this series, my series, converges or diverges together with this p integral. So I'd say, but this is a p integral. And we've shown previously, right? We've shown in section 7.8 that these p integrals converge if and only if p is bigger than 1. Hence the same is true for our series. And that completes the proof. So the schematic here we're applying the integral test to the series s equals sigma n from 1 to infinity 1 over n to the p. The related function is 1 over x to the p, because the an's here, the things that are being added up, is just 1 over n to the p, and if you swap n with x, you get this. We showed that that function is indeed positive, continuous, and decreasing everywhere on the interval in question. Therefore, by the integral test, our p series, oh, sorry, there should be an n, converges or diverges together with this p integral. Okay. But p integrals converge if and only if p is bigger than 1. Therefore, since this integral and this series do the same thing, and this integral converges if p is bigger than 1, diverges if p is less than or equal to 1, this series must converge if p is bigger than 1 and diverge if p is less than or equal to 1. So this result on p series is right up there with the result on geometric series in terms of importance. P series are only things like 1 over n to the p, summed from 1 to infinity or summed from 2 to infinity. Where the sum starts doesn't matter. But what matters is that the series, that the thing is inside, is just 1 over n to the p. Very, very similar to a p integral. Don't confuse the terminology. If I give you a p series and you tell me it's a p integral, I'm going to take off points, because series and integrals are different animals. But they do have a lot of similarities. And here we were able to use the fact that those two have a lot of similarities to say that these series, these p series, converge if and only if p is bigger than 1. What that means is these p series converge if p is bigger than 1 and diverge if p is less than or equal to 1. Just like p integrals formed an important basis for comparison when we were talking about type 1 improper integrals and the comparison theorem there, these series are going to form an important basis for comparison when we get our comparison theorem for series. And that's the next section. So before we jump to section 11.4, I'd like to do one more integral test problem. And normally at this point, I would ask you guys which problem you wanted to see, but y'all ain't here with me. I'm all by my lonesome this Sunday evening recording this for you. So I'm gonna zoom out a little bit. Give you guys the opportunity to write down anything you feel like you missed. Maybe zoom in just a smidge here so you can read a little better. And I'm gonna grab a problem. No, that shit's boring. That shit is also boring. All right, I lied. I've got two more problems for you. So this first example is an important example. It's a special case of a p-series. So we're not going to go through it all the way with the integral test. But there's a special example called the harmonic series. That's sigma n from 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4, and so on. Very, very famous series. This series diverges. Why? Because sigma 1 over n summed from 1 to infinity is sigma n from 1 to infinity 1 over n to the 1 is a p-series with p equal to 1, which is not greater than 1. Thus, by our result on p-series, the harmonic series diverges. Okay, I know that was boring, right? We just proved the thing for all p-series, and then here's like the most obvious of all the p-series, 1 over n. One of the reasons I'm showing you this is to provide you a counter example to one of the things we mentioned at the start of class. So why is this interesting? Well, remember what test for divergence says. So sigma n equals 1 to infinity 1 over n has an equal to 1 over n. The limit, the TFD, test for divergence limit here, and important, this is not the same as saying these things are equal. This is not the limit, the limit as n goes to infinity of an is not the same as the series sigma an, totally different things. Here, the limit of the an's, the TFD limit, is 1 over infinity, which is 0. But the series sigma an is sigma 1 over n, summed from 1 to infinity, still diverges. So you remember right at the start of class when I reminded you of what TFD says? It says if the limit of the an's is not 0, then the series sigma an automatically diverges. And people tend to get the wires crossed, thinking that the limit of the an's being 0 is the same as saying the series sigma an converges. It's not at all true. If this comes out to something other than 0, then the series automatically diverges. But there are many series where this limit does come out to 0, but the series still diverges. So the limit of the ANs being 0 does not guarantee convergence. And the harmonic series is the classic counterexample. All right, how are we doing here? Oh, I forgot to start my timer. So, quick look. Do I have a counter going here? Turn off my time. Don't. All right, we're going to go for just a little bit longer. A little bit longer, then I'll let you guys go. I promise one more integral test problem. Excuse me. And I want this one to be exciting. So let's say investigate the convergence of the series S equals sigma n from 2 to infinity 1 over n times the natural log of n. Here the series clearly not geometric. No hope for a telescoping series in any obvious way, right? That it's not a rational function, for example. You can't factor that bottom. It's not a polynomial. So the natural thing for us to try right now is the integral test. Here, f of x, the related function is 1 over x times the natural log of x. You just get it by taking the an and swapping the n for an x. Is this positive? Well, 1 over x times the natural log of x is greater than 0 if and only if. Again, here it's the reciprocal of something. The top is positive, so this will be true if and only if x times the ln of x is positive. I'm summing from 2 to infinity, so I'm looking for this to be true on the interval 2 to infinity. Certainly the x piece there is positive, and the ln x piece there is also positive if you remember the graph of ln x. I've tried to bludgeon this into your guys' heads in case it's not there yet. The graph of ln x looks like this. Okay, please get it in. If you do not remember this graph yet, you need to. This right here is 1, the x-intercept. So yeah, this thing is indeed positive, which is true for all x greater than 1, and certainly, therefore, for all x greater than or equal to 2. Check. Continuous. Well, again, as long as the bottom isn't 0. And where is the bottom 0? X ln x is equal to 0 if x is equal to 0, because this piece, right? Or if ln x is equal to 0. This is kind of just the natural thing to do. You've got a product of two things, trying to figure out where it's 0. So you set each of the two things equal to 0 on their own. Either x is 0 or ln x is equal to 0. Ln x is equal to 0 if you exponentiate on both sides. E to the ln x is equal to e to the 0. E to the ln x, so this piece, that's just x, and e to the 0 is 1. So the only two places where this thing could possibly be 0 are at 0 and 1, neither of which are in the interval 2 to infinity. So yes, it is continuous on the interval 2 to infinity. And in fact, x equals 0 isn't kosher for this guy anyway, right? Forget that it makes the 1 over x part 0. The ln of 0 is also not defined. So the only place we'd have to worry about for this is x equals 1, but I'm summing from 2 to infinity. So I'm checking that this is all true on the interval 2 to infinity. 1 and 0, neither of those guys are in the interval 2 to infinity. So now I need to check that we're decreasing. Here I'm going to get real sloppy, and I invite you guys to do the same. The function x is increasing. The function ln x is increasing. Therefore, x ln x is the product of two increasing functions. So a product of two increasing functions must be increasing. So x ln x is increasing. Thus, 1 over x ln x must be decreasing. Love that trick. All right, so my function here, 1 over x times ln x, is the reciprocal of an increasing function. Therefore, it must be decreasing. How do I know x ln x is increasing? Oh, well, x is increasing. Certainly, we know the graph y equals x. ln x is also increasing. If you don't remember that graph, I can remember it, but here it is. It's definitely an increasing function. Multiply two increasing functions, the result is increasing. You should prove that if you don't know it. Therefore, my function, 1 over x ln x, is the reciprocal of an increasing function, and hence must be decreasing. All right, so all this shit we need to do before we can do the good stuff. Now we can say, therefore, by the integral test, the series sigma n from 2 to infinity 1 over n times the natural log of n converges or diverges together with the integral from 2 to infinity 1 over x ln x dx, which is equal to the limit as r goes to infinity, integral 2 to r. I'll write it as 1 over ln x times 1 over x dx, because I'm thinking to make a substitution. In this integral, if I sub z equals ln x, then I'll get dz equals 1 over x dx. I need to also change my bounds. When x is equal to 2, z is equal to the natural log of 2. And when x is equal to r, z is equal to the natural log of r. So that integral is equal to lim r to infinity, integral natural log 2 up to natural log r, 1 over z dz. It's 1 over x dx, that is dz. This fella is lim r to infinity, natural log of z, evaluated from ln2 to ln(r). And now this is where I get to tell one of the worst jokes of all time. Brace yourselves. What sound does a drowning analytic number theorist make? I'll write out my limit here. The question again is, what sound does a drowning analytic number theorist make? log, 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 log. That's the sound. The sound of drowning analytic number theory snakes. Log, 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 log. All right, I'm sorry, had to do it. Expressions like this show up a lot in certain kinds of number theory, particularly analytic number theory. So does the integral converge or diverge? Remember, the series will converge if the integral converges. The series will diverge if the integral diverges. I've just done all this work to relate the series to the integral. Now I'm computing the integral, and I find that the integral which determines the convergence of my series comes out to the limit as r goes to infinity, log log of r minus log log of 2. Well, as r goes to infinity, we've talked about this several times now, the natural log of r goes to infinity. So this is ln of infinity, because this inside piece right here goes to infinity. Minus ln of 2. But the natural log of infinity, for the same reason the inside is infinity, is also infinity. So this is infinity minus log log, or ln of 2. Natural log of 2 is a finite number. So the natural log of 2 is finite. So infinity minus this finite number is still infinity. Thus, the integral 2 to infinity 1 over x ln x dx diverges. So the series sigma n from 2 to infinity 1 over n natural log of n must also diverge. Okay, that's it, lads and ladies. That's the result. This series diverges because we're able to use the integral test to relate that series to this integral, and this integral we were able to compute and show that it diverged. In general, this is about how most integral test problems go. You spend similar amounts of time showing that the related function is positive, continuous, and decreasing as you do computing the integral. Sometimes one takes longer than the other, but usually they're both fairly time consuming, which means I'm not crazy about this test. It takes a while. Every problem takes a while. So in the next video, I'm going to show you how to use the comparison tests. I'll go ahead and break it up into 2 because I didn't start my timer here. I thought that'll work out well anyhow. So yeah, this is the integral test. You should practice with it. Make sure you understand it. I want to give you a few little words of warning as we depart. The integral from 1 or wherever to infinity of f of x dx is not the same as the sum from 1 or wherever of an, but the two are closely related. So here, let me graph the sequence an. Maybe up here, this is a1. Maybe here, this is a2. Here, this is a3, a4, a5. Then if I draw some rectangles in, each one of these rectangles has width 1. So the area of the first rectangle is a1. The area of the second rectangle is a2. Area of the third rectangle is a3, and so on. If that sequence an is coming from the function f of x, then you can see how the area under the function f of x is related to the series. The full infinite series would be the area of the rectangles. So this is the integral from 1 to infinity f of x dx. And the rectangles themselves, all that area is the sum from 1 to infinity of an. So can you see that if the pink area is finite, the dark red area must also be finite? So if the integral converges, then the series must also converge. That's the most useful single picture for understanding the integral test. It's also how you prove the integral test. And if you look in your textbook at section 11.3, you'll find a rigorous proof of the integral test there. They draw this picture, and then there's a shifted version of this picture that you can use to show that if the series diverges, the integral diverges. If the series converges, the integral converges. So the result is that they converge or diverge together. They're very, very similar to one another. In fact, if you go on to take a class in measure theory, which is usually very advanced undergraduate or first or second year graduate level work in mathematics, you'll learn that there is a way to make these sort of things into these sort of things. Or if you prefer, to make these sort of things into these sort of things. But they're not the same, right? There are gaps here. There's area that's under the pink that's not measured by the red. So their values aren't the same. So don't tell me that they're the same. That's it. Okay, so I'll go ahead and end it here. I hope you guys have a lovely rest of your day. Make sure to watch the second video on the comparison tests. All right, that'll be coming right up. And as always, if you have any questions, you can contact me through Canvas. I will be doing my normal office hours, even though I'm out of town on my laptop using Zoom. So don't hesitate to reach out for help if you're getting stuck on something, okay? Take care, guys.